All right, Dr. Matthew J. Traum here with a mechanics of materials solution for you. In this problem, we have a 60 Newton meter couple applied to a steel bar as shown. There it is. And there's two parts to this problem. The first is we're going to assume that the couple is applied about the z-axis as shown. So they've got this guy as the z-axis and the couple's rotating around it that way. Determine the maximum stress and the radius of curvature for the bar. And then there's part B, which is basically the same problem over again, but assuming the couple is applied about the y-axis instead of the z-axis. And we're told that the Young's modulus is 200 gigapascals. Okay, so I always like to attack these problems with a plan. So what's my plan? I'm going to use two equations that I know to sort out what the stress is and what the radius of curvature is. And then I'm just going to basically solve the same problem twice with a slight change in geometry, which I'll show you. So we know that the stress is the couple multiplied by C divided by I, right? That's one of the equations we talked about in class. And then 1 over the radius of curvature is that same couple divided by E times I, Young's modulus times I. So the moment is given, right? There it is, there it is, there it is. So we know that one. C, we have to work out from geometry. E is given here. And really the big kind of problem here is having to work out I. But once we get I, it's the same I that goes into both of these expressions. And so we can work out both of those basically with, just sorting out I and looking at a little bit of geometry. So, let's work on I. So how do we get to I? How to get I? All right, so I'm going to cheat here a little bit. So what I've done is taken an I diagram from a table in a statics textbook. And notice here we've got this coordinate system, which is y, z with rotation around z. And here we've got y prime, x prime. And all I'm going to do is just walk in and change this guy from y prime to y, and that means here this guy gets changed to y, and here I'm going to change x prime to z, which means this guy gets changed to z. Most confusing part here is what's B and what's H and what gets raised to the third power and so forth. And so by doing this, I've now just basically mapped this shape where this is Z and this is Y onto this shape where this is Z and this is Y, and that eliminates any confusion about which is B and which is H, hopefully, as we solve the problem. So let's see what that does for us. So I'm looking for I around this axis, which I've called Z. So we'll call this IZ, and that's going to be equal to 1/12. Get my equation here, 1/12 BH cubed. And what's B? Well, B is the bottom, which is that thickness. So that's going to be 12 millimeters. And then H cubed, that's this height, which is 20 millimeters. And that's going to be raised to the third power. So if I crank through the math there, I get 8 times 10 to the minus 9 meters to the fourth. Now notice a little subtlety here. This is millimeters, this is millimeters, and all of a sudden I'm converting to meters. The reason I want to convert to meters is because the problem is basically laid out in meters, right? I've got a meters here, I've got gigapascals. A pascal is a force per meter, Newton per meter squared. So I want this in meters. So I'll leave it up to you guys to do that conversion from millimeters into meters. Okay, so now I've got my I. The other thing that I need to work out is the C value here. Well, what's C? Remember that whenever we have one of these beams that's bending, C is the distance between the neutral axis, the axis where there's no tension or compression, which in this case runs straight through the center of the beam, all the way up to one of the edges, right? So it's basically half the height of the beam because the beam is symmetrical. And so it's not 20, but it's 10. So I'm going to say C is equal to 10 millimeters. Again, half of 20 is 10. And I want that in meters, so it's going to be 0.01 meters. And now I've got all the pieces that I need to solve both of these equations for my stress and my radius of curvature. So let's do stress first. So my stress is that moment, which is 60 Newton meters, multiplied by my C value, which is 0.01 meters, and then divided by I, which I've just worked out is 8 times 10 to the minus 9 meters to the fourth power. And cranking through the numbers there, I get 75 times 10 to the sixth Pascal. So that's my stress for part A. I need my radius of curvature. So let's take this guy and solve for radius of curvature. So I've got 1 over radius of curvature is equal to 60 Newton meters divided by 200 gigapascals. And my I value, which I calculated, is 8 times 10 to the minus 9 meters to the fourth power. Should be a 9. There we go. Okay. And if I run through that, I get 37.5 times 10 to the minus third meters to the negative first power. But remember, this is 1 over radius of curvature. So the radius of curvature is 1 over this value. So 37.5 times 10 to the minus 3 meters to the negative 1 and 1 over that. And that gets me 26.7 meters is my radius of curvature value. Okay, so that's part A sorted out. And now we have to do part B. And part B is basically already set up for us because remember in the beginning, I cheated, right? I went through and I just took this chart and I rewrote where Y and where Z is. And for part B, we have to assume that the couple is applied around the Y axis. Well, here's the Y axis, which corresponds to my Y axis. And so all I'm doing is just saying, okay, the couple's no longer there. It is here around the y-axis, same value, 60 Newton meters. So all I really need to do is sort out a different value for I and a different value for C based on the fact that the couple is just moving around a different axis now. But I've already defined what Y is and what Z is. And so I can go down here and I can just use my equation for I sub Y, which, as you'll notice, just moves that third power exponent off of the H and onto the B. So that's a really simple, quick way to do it without getting yourself too confused. So I've got a clean slide here. Let me just reiterate that the couple's now this way, 60 Newton meters, and it is not here. And that this is Y and this is Z. And I'm going to be using this equation because my rotation is about the Y-axis. It's about there. Okay, so back to my original equations. I know that I, in this case, is 112 b to the third times h, which is 1/12. Okay, what's b? In this case, b is the base, which is this distance, right? This distance, which is 12. So provided I've done this right, 12 millimeters, that guy should get raised to the third power. And then h is going to be the height here, which is the height here, which is 20 millimeters. Now, as a sanity check, I expect a different value, right? So remember before when I did this, I got 8 times 10 to the minus 9. This time when I crank through the numbers, I get 2.88 times 10 to the minus 9 meters to the fourth power. Nothing's changed. The geometry is the same. All I'm doing is just rotating this guy around a different axis, but because it's thicker on one side and thinner on the other side, this I value is different. So the fact that I get a different value tells me that I'm going in the right direction. That's a sanity check. I need the value for C, which is the distance from the central axis, the neutral axis, to one of the extreme edges. Again, this guy is symmetrical. So that neutral axis, if I draw just a plane that represents that neutral axis, that's the plane. And the value of C that I'm looking for is no longer half the height. It's now half of the width of this thing. And so it's that distance is C. So remember, the width of this thing is no, the width of the, I was about to say 20. No, the height is 20. The width of this thing is 12. And so my C value is going to be 12 millimeters divided by 2, right? The distance from there to the edge, from there to there. So that's going to be 6 millimeters, which is 0.006 meters. So that's my C value. And E is still the same, right? 200 gigapascal. So now I've got all the information that I need to solve this guy. So my stress in this case is going to be my same 60 Newton meters. And now I need to multiply by my C value, which is 0.006 meters. And my new I value, which is 2.88 times 10 to the minus 9 meters to the fourth, goes in the denominator. And the stress that I get there is 125 times 10 to the sixth pascals. So there's my stress for part B. And the last thing I need is a radius of curvature. So remembering that the radius of curvature, 1 over the radius of curvature, is the moment divided by Young's modulus divided by I. So let's put in the numbers. 60 Newton meters divided by 200 gigapascals and divided by that same I value that I calculated before, 2.88 times 10 to the minus 9 meters to the fourth for this geometry. And what I end up getting is 104.17 times 10 to the minus third meters to the minus 1. Not quite finished here, because remember, my equation is 1 over the radius of curvature, and what I need is the radius of curvature. So to get the radius of curvature, I just take 104.17 times 10 to the minus 3 meters to the minus 1. That's in the denominator. I 1 over that value, and that gives me the radius of curvature, which is 9.6 meters. So that's my radius of curvature for part B. And I've got this one solved. Part A sorted, part B sorted. So that's it. Thank you for your time and attention to this problem.